So today, talking about Boolean algebra, we're going to zoom into NAND and NOR and their utility a little more today. As a gate, NAND and NOR have a lot of applications in both creation of other pieces of logic and direct applications as well. The one thing to note is a lot of large logical systems, like a processor in a computer, tends to be made out of as few different kinds of gates as possible. So you'll see a lot of logic made entirely out of NAND gates. And so what we're going to talk about today is how to build other pieces of logic, other gates, out of just one kind of gate, for example. And the Boolean algebra will let us sort those around as well. But that gives companies and engineers the ability to design one really good NAND gate, rather than having to design a really good of each kind of gate. And use that out to make everything else. Then we'll look at the rest of these are algebraic related laws. So hopefully you all remember algebra from math classes earlier in your life. We are using that same algebra today. However, it means a slightly different thing based on this course. So you'll recall when we introduced logic gates, the multiplication, or two letters side by side, is our AND operation. So multiplication looks like AND with ones and zeros. And the OR operation looks like addition. So we're going to see a lot of multiplication and addition mixed in with some other algebraic abilities. But that's how our logic gates are going to be represented numerically, is using those Boolean expressions we talked about earlier. So talking in general, what we're discussing is called combinational logic. So we're creating some sort of logic circuit out of multiple gates. It's a combination of multiple gates. We're calling it combinational logic. We have combinations of inputs going through that. But this is our combinational logic, and that is opposed to what we'll talk about later, which is sequential logic, which is timed by a clock signal. The logic we're discussing now is pretty much instantaneous. Whatever the state of those inputs is, will filter directly to the output. And they just happen. But if we look at this example, combination of logic gates B equals K and D or H and D, we can see if we factored out a D, well, if we look at just this top one, B equals K and D or H and D, how many gates did I just say when I read that? How many logic gates? Three. Three, exactly. We have two AND gates and an OR gate between them. Whereas if we factor out a D, which is just an algebraic operation, we have D ANDed with K or H. So how many logic gates in that one? Two, right? So very simple example here, but highlighting the point of using algebra to manipulate these. We can create a piece of logic, and when we translate that directly from our application in its most basic form, there may be a lot of redundancies or pieces of the logic we don't strictly need to produce an output. And so the algebra will let us cancel all that out. And by canceling it out, we lower the footprint, shrink the footprint of our circuit. We save money in fabrication cost and time. So this algebra is a powerful kind of circuit analysis and economic tool, the way we're going to talk about it here. Okay. So to do algebra, we have a number of rules and laws. So we love math, rules and laws. A lot of algebra heads here in New Albany for sure. I'm sure you guys love algebra out there in Kokomo as well. So we're going to introduce a couple of laws, 3 of them in fact, and then 10 rules. And then we'll have a nice table on how we can manipulate logic gates algebraically that we can apply when we're doing our homework and take a test and that kind of thing. So let's talk about the commutative law of addition. Commutative law of addition and multiplication. The order of our gates around an operator does not matter. So A or B is equivalent to B or A. It's pretty straightforward just based on our logic gates as well. So you can flip the order of those two and it means the same thing. Same is true for multiplication, which is our and operation. So A and B and C is equivalent to B and C and A. So we can move around variables in that way. We also have the associative laws of addition and multiplication, meaning we can group portions of a series of operators. So A or B or C as a quantity is equivalent to A or B as a quantity or C. So what that looks like physically is the order that we stagger logic gates in. So when I read those just now in English, the way we would graphically show that would be like A or B quantity ORed with C. And so physically, this is equivalent to this, where we just reordered the order of those logic gates, but the operations remain equivalent. And the same is true for AND gates. A and the quantity B and C is equivalent to AB quantity. So this is AB quantity ANDed with C. This is A ANDed with the quantity BC. So you can move those parentheses around, but identical to your algebra, the result remains the same. We also can distribute. So this is everybody's favorite math property, hands down. We can distribute, and we can also extract variables if it's common between each term. But A and the quantity B or C, you can distribute the A across that and get an equivalent result. Logic gate wise, this is what you're doing, is taking those combined logic gates, and this is the example from a few slides earlier, and expand it into its basic form here. One note about this form, and we'll see it frequently, if we're down to just term plus a term plus a term, we're calling that a sum of products. Sum of products. So what is a sum? Addition, adding things together. What's a product? Is the multiplication. So this is the sum of product terms. That form, the sum of product terms, we're going to use it a bunch today. Like this is the sum of products. But in next week, we're going to talk about another simplification technique, method, that requires us to jump off from a sum of products. So we'll do a little bit of algebra and then apply something much more powerful next week. But we're sticking to the basics for today. So that's it for the laws, though. We have the commutative, associative, distributive laws. So let's talk about rules. You guys love rules. Rule number 1, anything ANDed with 0 equals 0. And all of these can be proven using the truth tables from previous. And there will be a summary table included here and included on any homework and test. Well, the homework, I expect you to just find it yourself. If I have you do algebra on a test, I'll give you the rules and laws in a table format as well. That you'll see in a moment. So rule 1, anything ANDed with 0 equals 0. Anything ANDed with 1 equals itself. So rules 1 and 2. Anything ORed with 0 equals itself. Anything ORed with 1 is equal to 1. And side note as to why we're defining these give us abilities to cancel things out or drop them out of our equations to make them smaller and more condensed, remove redundant parts of our equations. And so that's why we're introducing these. Anything ANDed with itself is equal to itself. Anything ORed with itself is equal to itself. So we'll have that ability to reduce equations. Anything ANDed with its complement equals 0. This may be a new type of symbol we haven't talked about yet much, although it's, I think, appeared a few times. The bar over a letter is the invert operator for algebra. We've occasionally shown it as a single quotation mark, or shown it, we've seen the not gate. But when we're working with letters algebraically, the bar over top means invert of that letter. And it can be used for the purposes of grouping. So if you have a bar over multiple terms, like a NOR gate, which would be A or B, the whole thing inverted by the inversion bubble, I don't have a NOR up here to point at, but you can group the whole thing with the bar. So we're going to be able to group AND and NOR together. We'll see that in a moment as well. So that's 7 and 8, and in ORed with its complement. And what happens? Anything ORed with its complement equals 1. Anything complemented twice will return to its original logic. So when you're out in the world trying to outwit your siblings and you call something out for being a double negative, that's what we're talking about. If you invert, then invert it again, we're back to the original value. We can use that for canceling out bars as we simplify algebraically. And rule 10, the most confusing one by far, although it can be kind of proof, it has its proof in the truth tables. It's a powerful manipulation, but it's not entirely intuitive. But A and not A, B, so A or A not and B is equal to A or B. And so we have a way of eliminating a partial term if you have a letter and its complement ANDed with something else. A letter or its complement ANDed with something else. We have a way of eliminating a part of that. This is by far the hardest one to identify. All the other ones are pretty straightforward. You see the 0 or the 1 and we know what to do. This one, when it shows up, can be tricky, but if you see the same letter, kind of in this structure, we can use that to eliminate parts of our algebra as well. So here's your table. This table will be included for you on your tests. For example, test 2, you'll have to do this in some small part along with some follow-up material. But you'll be given this anytime that you may need to reference it. So as long as you are comfortable using your algebra, you're good to go. Examples. Let's look at an example. A couple quick thoughts. Which Boolean laws are illustrated below? I took the table away. I need to post it over here or something. But if we're putting parentheses around different parts of this, B or D or E is equivalent to B or D or E. Which rule or law would that be? You can just tell me law or rule and a number. Law number 2, which was what was the name of law number 2? Associative, yes. Then we said A is equal to BA. That is law number 1. ABC is equal to BCA. That was also law number 1. Then A can be distributed over this quantity C or D. We have that law number 3 in effect there. We'll look more at the rules here in a minute with some other examples. But what are some strategies for remember the 10 Boolean laws? This is a great question. There's one master strategy that I would encourage you to employ every time. Use the table. All right? And you'll remember all 10 with ease. So, simplification is not just an exercise in algebra, which I know you would be enthusiastic to do, even if that was the only reason to do it. But equivalent circuits can be formed with fewer logic gates. Depending if you're the one building the circuit, that may have increased importance to you. Cost is reduced by reducing the number of gates. Reliability and components that can fail are removed. And then we have rules and laws of Boolean algebra. And by applying those, we're reducing our overall footprint as well. So we're using less of a piece of silicon where we're making our microchip for a certain number of gates. Okay, so simplification of circuits. Let's start here. Let me find my sheet. So let's see, this is the example I'm looking at. Yeah, it is. Okay. So let's see how this looks with the screen up. Get there and we'll go from there. Okay. So hopefully we have a decent marker here. When we're looking at creating a simplification of our logic gates, here's a logic gate circuit shown here. We first, before we can begin simplifying, we need what is the equation overall for this circuit that we have here, which is what is the equation for x. So we need to find x equals, and we create the equation for the circuit, starting at the inputs and moving left to right, building out each logic gate. And you can write those on your schematic. These have been written for you, but in the future, we're not going to have that scaffolding step. But you can see A and B going through an OR gate gives us A or B. B and C going to an AND gate gives us B, C. And I'm just writing those at the output of each logic gate. So then we AND those two items together. We have the quantity that's all coming into one input. So we know that's the same quantity, A or B. And then we have BC on this end right here. We don't have to put parentheses on the BC term because as a quantity, we can rearrange that because of one of our laws allows us to, split the position without a problem. But then we have that quantity going through an OR gate. We have A or B and BC, or we have A going in the top input, A or this piece right here. So X overall is equal to A or B times BC. Okay, so question number one is, when I go out of our illuminated square, Kokomo, can you still see my marker over here? All right, yeah. We're good. You guys must have blown up on a big screen. I love it. Okay, question two then is, how do we simplify this to save gates and save space? So looking at that algebraically, what is something about that equation that jumps out at you immediately that might be a way to simplify, a route that we could go? What would your step one be?
Multiply BC parentheses.
Okay, distribute out this BC. So let's start with that. A or, we're going to distribute out the BC. So we'd have ABC or BBC. What about that side of the expression there is now suspicious and something we can cancel out? Feels like it shouldn't be there. What was that?
Double B becomes just a singular B.
Yeah, we have our B here. If we see a term side by side, we know that's probably something we can cancel out. B ANDed with B. We would then say, okay, what happens in that case? So we go back to our table. B ANDed with B. Where's that at?
B.
Follows this form. Just equals itself, right? Rule number 5. So we have B ANDed with B. Just equals itself. So A or ABC or BC. What do you want to do next? Anything else? See any movements we can make? Remember that our laws can apply in both directions. Well, that's a hint on the next step as well.
I was thinking, like, if you would do it algebraically, if you put A to the other side and then take out a B from each term.
Well, we don't want to go to the other side at all. We have to stay all on this side of the equal sign.
Would you, so you can factor out anything?
Yeah, let's do that. Factor out something. What do you want to factor out?
I was gonna say BC.
Get the BC out of there. Okay, so we just distributed the BC. Let's factor it back out again now that we canceled part of it and see what happens. So I'll factor out the BC. that leaves us with A plus 1. When we take the BC out of ABC or BC, take the BC out, we're left with A plus 1, or A or 1. Anytime we see a 1 or a 0, we know that's something we can take action on. So anything plus 1 equals 1. So we're going to be left with a 1 in here. What's anything times 1?
1, so BC.
Is itself, yeah. So we can apply both of those together. So that condenses down to 1. BC times 1 is just BC. And so applying those two rules at once leaves us with A or BC. How many logic gates are required for A or BC?
3.
I heard 3. I heard 2. Who seconds one of those answers?
I think
And you say 2. Okay, yeah, we need 2 logic gates, right? We need A or B and C. So that's 2 logic gates required to produce the identical logic that this X contains. So we're not showing it right now, but we will in some of our lab examples. But if we made a truth table for X out of these 2 circuits, they're identical after going through the simplification process. And the reason that it works like that is by eliminating things, we're just eliminating redundant logic that would have resolved to the same thing. So we eliminate all the redundant logic. We've cut our number of gates in half, which means you've cut your cost potentially significantly. And you've made your boss at whatever circuit design company you're at very pleased with this work you've done. So any questions on that process before we click to the next one? All right, let's do it again, but with less help. And one kind of good thing about our class arrangement here is all of this will be recorded. So you can go back and watch these examples if you want to. You can also find additional examples in your book or on the textbook, for example. And you have access to these slides on Brightspace. So let's get an equation for this circuit. So we have A and B as an input to this gate. What would the output be? Yep, A or B. How about this one?
BC.
BC. All righty. So we have A or B and BC going in here. So what do we have at the output for W equals?
parentheses A or B, close parentheses.
Yep. A or B, close parentheses BC, which we note is similar to part of the previous circuit, but it's missing an additional connection. But now we can apply our simplification. So we can do what we did last time, which is just multiply out the BC. ABC plus BBC. You know, the BB just becomes B. We can take the BC back out. So let me write that out. ABC plus BC. Plus, take the BC back out. And we have the A plus 1. A plus 1, condense it down to 1, and we're left with just BC as the simplified circuit of this form. So again, maybe you had a physical reason why part of your instrumentation panel had this logic and number of buttons, part of your instrumentation panel had this. You combined it together in your master controller and it looked like that. So it made sense while you were building it out physically. But once you got to the end stage and you want to make it on one condensed FPGA or printed circuit board, that's when you can do a simplification. And part of our lab activities, we'll look at some automated tools for doing that. And we'll also look at some other ways of simplifying as well coming up. But that's the process that we're talking about just today, which is strictly algebraic. So, okay, let's move on. Everybody good with that? Okay.
I have a question. So
Sure.
if the resulting gate would just be BC, so like an AND gate, if you needed like 3 push buttons for gates, you wouldn't be able to use just the AND gate, right?
Well,
Like,
yeah,
what
excellent.
happens to A?
So do the students speaking come through in Kokomo too, or I'll restate the question? It is, okay, yeah. So what happens, what's that final gate actually look like? It's just B and C. We have switch A over here. What that resulting gate looks like is, an AND gate, of course. And that was W. And we have inputs B and C required. B and C. And so the question was, that didn't require the A term anywhere. And so what happens? A is unused in this case. So that means your panel, instrumentation panel, for example, was over-designed. And what that would mean is if you looked at the truth table, you could go to that truth table and flip A on and off, and it would not impact the output. So A is an entirely redundant control in this particular case. It does not impact the output ultimately. So when you go to the truth table, you'd look for any combination of B and C. It would be the same if A was 0 or A was 1, meaning A is not impacting that output. So this can also reveal you added a $500 push button to your instrumentation panel that literally does nothing. So it is a design, a choice to help with your design, to find things that may not be necessary. Good question. Any other thoughts? All right. So let's move on slightly to our next short piece of algebra. We have one more tool we need in our algebraic tool belt. This one is quite powerful, and it allows us to integrate our NAND and NOR gates. So algebraically, this manipulation is called De Morgan's theorem. It's used to simplify circuits with NAND and NOR gates. Remember that I mentioned the inversion in a NAND or a NOR is a grouping symbol, essentially. So the bar over A and B groups those together. The bar over A or B, so this is a NOR, groups those together. For simplification purposes, it is occasionally useful to separate the NOR operation or the NAND operation. We want to break the bar up to cancel out parts of it. We don't want the whole grouping together. So De Morgan's theorem allows us to do that. It's 2 steps. If you want to separate a NAND or a NOR, you have to break the bar and then flip the operator. So if we have a bar and we have A and B, we break the bar and flip the operator to not A or not B. So logically that is identical, but algebraically, we now can move the A naught and B naught around to do other cancellations, manipulations, so on. For the NOR, we have A or B knotted, the whole thing knotted as a quantity. Break the bar and change the operator from AND to or to AND. So break the bar, change it to A and B. So it's A naught and B naught as separate quantities. So that's how we'll apply De Morgan's theorem, which again, these are your NAND and NOR gates that we're working with, which are a common building block for a few reasons. So those rules I just said, break the bar over the variables, change the sign between them. And you could graphically, draw those out and compare the truth tables, they would be the same. Okay, so before we get into using that as an example, just some notes. NAND gates and NOR gates are considered universal gates because you can build all the other gates out of those. As an example, NAND can be used for an inverter. Just by tying the A inputs together, your NAND will now operate as an inverter. So if you go take your great new job right out of school at Intel to design the best possible cutting edge NAND gate in 2025, If you also want to design an inverter, you've now doubled your workload and your employer has to pay you more for all those hours. However, if your perfect NAND gate or near perfect NAND gate can be used as an inverter, you ultimately save design time as you dial in your process for creating this physically. You save process design time. You may have special machines specifically configured for that process. And so ultimately in manufacturing, big scale, doing the same thing over and over again, just like in our C programming class, we just learned loops and we said computers love doing repetitive tasks. Manufacturing units love doing repetitive tasks physically as well. And as you get more computational tools, they're getting a bit more dynamic, but in general, if you can design one thing really, really, really well and use it for multiple different interfaces, that is a great and efficient, economically efficient goal to go for. So NAND can be used as an inverter is point number one. You can prove that algebraically. You can prove that with truth tables. You can prove it experimentally. You can also make an AND gate with two NANDs, for example, because you know NAND is just an inverted AND. So we can make an inverted AND and then use it as an inverter to make AND out of NAND. All right, so you have NAND-based logic. Algebraically, you have two inversion bubbles that you can cancel those bars and leave us with just A, B, AND. You can make OR with three NAND gates. And you can work through that algebra. It's slightly longer, but using De Morgan's theorem, you can solve all that out. Basically, you have an A and B not going into this NAND gate. So break the bar, change the symbol. You're going to have two bars over each that you cancel out, and you're left with an OR gate out of three NAND gates. You can make a NOR gate out of four NAND gates. I don't think there's any more after this, but you can make any gate out of the NAND gates. For example, NOR gate has equivalents as well that I think your homework has you figure out one or two of those. Just kind of puzzly to see how do you form one gate out of the others. But you can make NOR with four NAND gates. So it's setting up using NOR as an inverter here. Your homework will have you look into making some other logic gates with that. So you just get to play around with those truth tables. Think about your algebra. Algebra gives you the key to have I solved this problem or not. And that's where I'm ending today. So on Wednesday, no, what's today? Tuesday? On Thursday, we have our lab, 100% lab. And your homework, where's our calendar here? Homework 2 is due, coming up on Tuesday, so a week from today, which means we also have homework 3 assigned. So homework 2 is due on the 16th, homework 3 is due a week after that. So kind of have the two homeworks going on at once, but yeah, do homework 2 and 3. Homework 3 will contain, I think, some of next week as well. We're not going to add a homework 4, it's just homework 3 continued. Our lab is going to deal with Boolean reduction primarily. Next week, we learn another technique for Boolean reduction that will give us a much more powerful tool for moving from sum of products to the end without doing a ton of algebraic steps. Because as your circuits get bigger and bigger, there's a lot more algebra involved.